Alright guys, so in this video we're going to talk about elastic collisions. So in the previous lessons we looked at inelastic collisions, so collisions where the objects stick together. And as I mentioned, in an elastic collision, the momentum will be conserved, but the kinetic energy won't. To contrast with that, we have elastic collisions. Now, in an elastic collision, the collision occurs, and both the momentum and the kinetic energy, the total kinetic energy of the system, are conserved before and after the collision. And so when these collisions occur, what you'll notice is that the objects will bounce off of each other. Okay, so they don't stick together, they separate after the collision. And so what I wanted to do is I wanted to go through, what's a fairly straightforward problem with an elastic collision. And so consider two balls, one red and one blue. The red ball has a mass of 3 kilograms. The blue ball has a mass of 2 kilograms. And then you can see the initial velocities on the screen here. And so the question we want to answer is, what are the velocities of the balls after the collision? So looking at that, what we'll notice, and we're going to use this fact, that momentum is conserved. So what I can say is that the momentum before the collision has to equal the momentum of my system after the collision. So the momentum of my system will be the sum of the momenta of both of the balls. You can see up here that my coordinate system I've defined to the right as being positive, so this initial momentum will be positive as well. So the initial momentum, the momentum before, will be 3 kilograms times 5, and then this will just be 0. And then that's going to have to equal the momentum of the red ball after the collision, which is the mass times the velocity of the red ball, plus the mass times the velocity of the blue ball. And at this point, we have two unknowns in our equation. And as you guys learned, or should have learned from algebra class, when we have two unknowns, if we have two equations, we can solve for them. And so that's where this conservation of kinetic energy comes in. So what I'm going to do is I'm going to say that since I know that the kinetic energy of the system has to be conserved, that the kinetic energy before, again, this is the kinetic energy of the whole system, and since the red ball is the one moving, this will be the kinetic energy of the red ball, has to equal the sum of the kinetic energies afterwards. Now notice, because energy is not a vector, I don't have to worry about positive or negatives for these velocities, but that will come out with the conservation of momentum. So I now have these two equations. And I'm going to need to solve for them. So we have two equations and we have two unknowns. And what I'm going to do is I'm going to use this conservation of momentum equation. And I'm going to solve for the velocity of the red ball in terms of the velocity of the blue ball. So you can do the math yourself if you want. But using algebra and solving for it, we'll get this expression for the velocity of the red ball. Then what I'll do is I'll go back and I'm going to substitute this expression right here into the conservation of momentum, the conservation of kinetic energy equation. And so this equation right here came from this, and you just square it, and so I'll get that equation, which, it does look kind of gnarly, but you can simplify it, and just kind of do algebra here, but you can simplify it, and it does simplify to this equation, kind of this pink box right here. So this is the equation that I want to solve for. It's a quadratic, so I can use the solver on my calculator, and I can solve for the velocity of the blue ball. And so doing that, I'll solve for VB, again using my calculator, and I'm going to get two numbers. I'm going to get 3.31 meters per second, and I'm also going to get 11 meters per second. So I have two possibilities for the velocity of the blue ball. And you'll see this very often in these collision problems because, again, we're solving for quadratics, and quadratics have two roots on them. One of them is physically reasonable, and the other one's not. So these are the two possibilities, and so both of them would say that the blue ball would move to the right, which, again, makes sense to us. But if it has a velocity of 3.31 and I plug it back into here, I'm going to get a velocity of the red ball of 2.79 meters per second in the forward direction. Whereas if it has a velocity of 11 meters per second, the red ball will have to actually move backwards. It's going to have to actually move backwards in the negative direction. So looking at that, and kind of realizing that if it's 3.31, then this will move forward. If it's 11, it's going to move backwards. Because this is more massive, it makes sense that after the collision, this will continue moving forward. In fact, it will continue moving forward, and it's going to be moving more slowly than it did before, which again, it makes sense. So it stands to reason, let me grab a different color here. So it stands to reason that this is, it's a messy line here. But it stands to reason that this is the most physically reasonable answer. Okay, right there. And so the final answer to the problem would be the blue ball will move away at 3.31 meters per second. The red ball will continue moving forward at a slower velocity. And these numbers satisfy both the condition of the concentration of momentum and the concentration of kinetic energy, which again is what we have to have in an elastic collision.